Hi, this is Tom Reardon, math teacher from Ohio, ready to join you in doing the plastic straw activity. And the first question is, how many straws are used in the United States each day? So again, how many straws do Americans use every day? The number should astound you. Many end up in the ocean along with plastic bags, where sea life accidentally consumes them. Nearly 90% of the debris in oceans is plastic, sad to say. So how many straws do Americans use every day? $500 million. 500 million? Oh my. So to help us comprehend that number, 500 million straws per day, let's investigate this in some kind of context. Please note, we want you to use a calculator to do your calculations. And we want you to store each intermediate answer into a different variable on your calculator. Make note of that variable on your paper with the solutions. Please don't round any intermediate answers, but round only final answers to 3 decimal places. You'll need a piece of paper and a calculator. Be prepared to pause the video as needed and do it as asked, then continue. So here's the plan. Students do this problem as if you were in a math class along with your teacher teaching. As the teacher, I'll pause often and ask you to do something. Pause the video. Please do that, or at least attempt that something. Then resume the video and continue. The plan is for you to try it first, then continue and make corrections as needed. You can download the student PDF at this website, or you can just use your own paper. That's your choice. So let's get started. So exercise number 1. If we connected these straws for one day, tip to tip, and could place them along the equator, how far would they wrap around the Earth at the equator? Now it asks you to discuss in your groups what information you need to know in order to solve this, but you don't have a group, sorry. This is as if it was in class. So I want you to think about that. Pause the video, do what is asked, resume when ready. So go ahead and do that. So some possible questions. What straw length should we use? So I researched this, and for this problem, we're going to use an average length to be 7 3/4 inches. We also might need to know the radius, diameter, or circumference of the Earth. That would be a good question to ask. And so I researched this online and found out that the Earth is not a perfect sphere. The rotation of the Earth causes it to bulge at the equator. And so the diameter from pole to pole is this number, about 7,900 miles, while the diameter at the equator is a little bit bigger, 7,926 miles. So for this reason, Earth is called an oblate spheroid, a sphere that experiences flattening at the poles. And so we're going to use the equatorial diameter for our calculation. So this is our diameter for our calculations right here. So getting back to exercise 1, we talked about this. These are the 3 numbers that we need. This is the information we need to decide in part A. And so now it's time to solve the problem. So pause the video and give me your best shot right here. Okay, please give me your best shot and resume when you're ready. So again, the question is, if we connect these straws for one day and place them tip to tip along the equator, how far would they wrap around the Earth at the equator? So what we need to do is multiply 500 million times the length of one straw, and this is how many inches there are, and we're going to store that in A. So let's go ahead and see what that looks like on our calculator. All right, so in the calculator, I'll type in 500 million times 7.75 for 7 3/4 inches. And we get this huge number, 3 trillion something inches, okay? And I'm going to store that. I'll press the stow key, and then alpha math to get the A key, alpha math to get the A key, and press enter. And now A has that value right there. And so here's the screenshot for that. We need to convert that to feet, so I need to divide what's in A by 12. So let's bring up the calculator for that. Alpha math to get the A, divide by 12, enter, and that's in feet. And I'm going to store that into alpha apps for the letter B. And now B has that value in it. And there's the screenshot for that. We need to convert that to miles. So I'm going to have to take that, what's in feet, and divide it by 5,280, because that's how many feet are in a mile. So I'm going to use, let me bring up the calculator. So I'm going to press alpha x t theta n to get a fraction. Alpha apps for the letter B, down arrow, 5,280, and then press enter, and there's that answer. And I'm going to store that into alpha program for the letter alpha C. And again, there is the screenshot. The circumference at the equator, this is the diameter, so diameter times pi is the circumference. So I need to multiply that diameter times pi, and I don't want to use 3.14, I want to use the actual pi, which will as many significant digits as I can get. So let me type in 7926 times, and then second caret gets me the pi. And we'll go ahead and store that into alpha D, alpha matrix, which is, or alpha x the inverse, which is D. Oops, forgot the store key. And so that looks like this. So one day's supply of straws will wrap around the earth how many times? That's what I want to figure out. So I have to take what's in C, how many miles of straws, divide it by the circumference. And so let's go ahead and do that. Again, I'm going to say alpha x t theta n to get the fraction template. Alpha program for the letter C, down arrow. Alpha x inverse to get the letter D. And so it's going to replace those values and divide them. And I'll store that into alpha sine, which is the letter E. And so it's almost 2.5 times in one day the straws will go around the circumference of the earth. All right, so pause the video, make any corrections you need to make, and resume when you're ready, because we do need these numbers as we go along. Exercise 2 is an extension from 1. If we connected these straws for the entire year and can place them tip to tip along the equator, how far would they wrap around the earth at the equator? Pause the video, please do this, and resume when you're ready. So for the solution, I just have to multiply what we got in E before by 365. And so let's go ahead and do that with our calculator. So 365 times alpha sine for the letter E. And so almost 896.5 times wrapped around the earth. Exercise 3, if we connected these straws for the entire year, it could place them on a straight line from the Earth to the Moon, how far would that make it to the moon? So again, I want you to think about this, what information you're going to need to know in order to answer this question. Think about that. Pause the video, do what is asked, resume when you're ready. So possible questions that hopefully you thought of. What is the distance from the Earth to the moon would be a good question. And so I looked this up and came up with this information, and I'll put this on the next screen. Well, by the way, I found out the moon is moving away from the Earth at a rate of about 1.5 inches per year. Just FYI. So at its perigee, the closest distance, the moon is this many miles to the Earth. At its apogee, the farthest distance, the moon is this many miles to the Earth. So the orbit is not truly a circle. Okay, the radius is not always the same. So on the average, the Earth are about this many miles apart, 238,855 miles. This is the number we're going to use in our calculations. So from the Earth to the moon, that's how many miles it is. So getting back to exercise 3, if we connected the straws for an entire year, placed them tip to tip on a straight line from the Earth to the moon, how far would they make it to the moon? So there's the information we needed to know. I want you to solve the problem. So pause the video, give it your best shot, resume when you're ready. All right, so for the solution, we're going to use information we found in exercise 1. So the length of straws in miles is stored in letter C. And what we need to do is divide that number by the average distance to the moon, which was this many miles. So this is the calculation we need to do. So let's bring up our calculator to do that. And here's what was a good idea to have those numbers typed in, because we have so many significant digits there. We don't have to retype them, might not make a mistake, and so on. So alpha x t theta n gives me the fraction template. Alpha program brings up the letter C. Down arrow, type in 238,855 miles, which is the distance from Earth to the moon on average. And we're getting about a quarter, a little bit bigger than a quarter. And we're going to store that into alpha tangent, which is the letter G. And this is our screenshot there. The length of straws in one day will go a little more than a quarter of the way to the moon. For 1 year, we need to multiply this by 365. So let's go back. 365 times alpha G. And I'm going to store that into alpha H in case I need it for some other calculation later. And also write that down on paper so that I don't forget where it is. And this again is what the screenshot looks like. So the length of straws in 1 year can travel the distance from Earth to moon almost 93.5 times. And that would be almost 47 round trips. Earth to moon, moon back to Earth. Exercise 4. If all these straws were made of plastic, and not all 500 million are, but let's say they were, what would be the volume of the plastic used to make the straws for 1 year? So you need, again, to think about what information you need to know in order to be able to solve this problem. So go ahead and think about that. Pause the video, think about that. See if you can come up with a couple things you would need to know. Resume when you're ready. So some of the possible questions are the dimensions of the straw. Like we already know the length. What about the outside diameter? What about the inside diameter? What about the thickness of the straw? Those are things that we would need to know to be able to figure out the volume of a straw, of the plastic that makes it up, that is. So again, we're going to use that average straw, 7 3/4 inches long. The outside diameter of the straw, a normal average straw I should say, is 3/16 of an inch. And the thickness of the straw material we'll use is going to be 1/100th of an inch. So now that you've got this information, you should be able to solve the problem. So pause the video, give me your best shot, resume when you're ready. All right, so let's go ahead and look at the solution here. If these straws were all made of plastic, what would be the volume used to make the straws for 1 year? So one way to visualize the volume of the plastic contained in one straw is to cut the straw along a vertical line and flatten it out to be a very thin rectangular solid. So if I do that, I'm going to have a flat rectangle here that the length is 7 3/4 inches and the width is the circumference of whatever the straw is. And then we have the thickness of the straw as well to make it a 3D figure. We have to calculate the volume of this rectangular solid, but we first need to calculate the circumference of the outside of the straw. So the circumference is pi times the diameter, so that's going to be pi times 3/16 of an inch. So let's go ahead and again bring up our calculator and multiply pi times 3/16. So pi is second caret times, and then the fraction template alpha x t theta n, 3/16. Enter. And that is in inches. That's the circumference of the straw in inches. And I'm going to store that into alpha letter I, which is the x squared key. And so there's the screenshot showing those calculations. The volume of plastic needed for 1 day's worth of straws, well, since this is a rectangular solid, the formula is volume equals length times width times height. And so the length is 7 3/4. The width is that value we just came up with for I, that circumference. And this is the thickness or the height of the straw. So let's go ahead and bring that up. So that's going to be 7.75, other parentheses, alpha x squared for the letter I, and then 0.01. We'll check that, and I'm going to store that into letter J. So store alpha, the comma key gives me the letter J. And that's what that would look like. Not much volume there in one straw, is it? But we would like the volume of all the straws, so we have to multiply that by 500 million, and that would be the volume for 1 day of straws. And so let's go ahead and do that. So that's 500 times alpha comma for letter J, and I'll store that into alpha K, which is above the parentheses. So this volume is in cubic inches. We need to convert that to cubic feet. So we need to divide this not by 12 and not by 12 squared, but need to divide it by 12 cubed, because 1 cubic foot is 12 times 12 times 12 cubic inches. So let's go ahead again. We need to have a fraction template. Alpha k is where I have the value stored, and I want to divide that by, down in the denominator, 12. The caret is the exponentiation key to the third power. And we're going to go ahead and store that into alpha right parentheses. So it looks like that. This is the number of cubic feet in a day. We need to do this for a year, so we're going to need to multiply that by 365. Wow. So 365 times whatever it is in the letter L, and I'm going to store that into alpha m, which is alpha division. So let's try to comprehend what this volume of plastic for 1 year means. So to put it in some kind of context, something we can visualize. Here's, what is that? 4,821,386.837 cubic feet of plastic. Okay, think about foot by foot by foot, almost 5 million of them. So what we want to do here is, if we were to take a football field and cover it with plastic, melted plastic, from goal line to goal line, from width to width, what would be the depth of the plastic in 1 year? Okay, so there's our question right there. Now, a lot of people don't know what the width of a football field is, and neither did I. I had to look this up. And it turns out to be 160 feet wide, which isn't even a whole number of yards, which surprised me, but that's pretty much what it is. So the solution. All right, so you're going to need to pause the video, give me your best shot on this, and resume when you're ready. So what we need to do is calculate the area of the football field in square feet from goal line to goal line and sideline to sideline. And so we know it's going to be 100 yards or 300 feet. And we just told you it was 160 feet wide. So we multiply length times width to get that. And I'm going to store that into alpha n. So 300 times 160. And store into alpha log, which is the letter n. So it should look like that. We need to divide the volume by the area to find the height. Remember, length times width times height. So we need to divide by the length times width to get to the height for the depth of the plastic. So that would be what we had in m divided by what we just found in n, and that will give me the height of this plastic box, so to speak, solid here. So let's again here bring up the fraction template, and that's going to be alpha division down divided by alpha log, which is n, and I'll store that into the letter O, which is alpha 7. And that would be in feet, almost 100.5 feet. So picture this on top of a football field. This is the from goal line to goal line, sideline to sideline, and this is over 100 feet tall. Now picture over 100 feet tall, 10 stories, okay? So this is what 4,821,386.837 cubic feet of plastic would look like. And this is what we use just in straws in the United States per year. Where does all that go? So all materials can be found at this website. You need to contact me. There is my email address, and I hope this was worthwhile for you.